Gareth, and nice to see so many people here at the run-up to lunch, so try not to distract you from that. Right, so to get the first and most popular question out of the way, what is ETAS all about? Well, ETAS stands for Empowering Tomorrow's Automotive Software. And we develop a lot of tools to help people build cars, hence the 3.5 billion copies of our operating system driving around on the streets today. And when we think about AI, typically in vehicle systems, in the presentation from ARM earlier, think about AI, about chatbots and generative systems and things like that. These relate to things like computer vision in ETAS, so perception systems, where you're talking about massive computational resources, effectively infinite resources if you're an old school embedded developer like me, used to working in assembler on 8-bit micros. So what I want to talk about today is how can we bring the benefits of machine learning and AI into these traditional real-time embedded systems, of which there are going to be lots of them still in cars, but in all sorts of other industries as well. And the particular tool I'm going to be talking about comes from our mother company, Bosch, because they built a semiconductor fab. They weren't happy with the behavior of the handling robots. They wanted to upgrade that using machine learning, and they developed a tool to do that without having to redevelop all of the control systems around that. So what I'm specifically focusing on is small systems with very much finite resources. And with these small systems, one of the key drivers is always cost. How can we remove things and simplify the bill of materials to make it cheaper? And I don't think in any industry that's ever going to go away. So one example that one of our customers is working with is the hands-on detection in your steering wheel. So when you've got your adaptive cruise control on and it's doing its lane keep assist, and the steering wheel will start flashing lights at you if you're not paying attention and being ready to intervene if necessary. So today that's often done with capacitative sensors in the steering wheel, but actually people have realised you've got your whole steering set up, and especially now with steer-by-wire systems, there's a lot of instrumentation in the steering gear. You've got all of the information about the vehicle speed, direction, the torque on the wheel, the torque on the suspension setup. So you can use that data to create a model to say, is this torque coming from the driver having hands on the wheel, or is it just feedback from the vehicle travelling on the road? So you can replace the steering wheel sensor with the sensors that already exist in the mechanical system. So we're switching from a physical to a virtual sensor in order to save cost, and using machine learning to do that. So another example comes from ultrasonic parking sensors. So again, we're working with a team. They've been developing this system for nigh on 30 years. And as you can imagine, it's developed into a huge mess of spaghetti code that nobody understands. And the guys who originally started working with it are now at retirement age, or they've been promoted or whatever. So they're a younger team coming in, starting to look at it and saying, we can't make head and tail of this. We're being asked to argue about it for more and more stringent safety assessments, quality assessments, and effectively nobody can say what's going on. And the other part of it is the manufacturers are saying, if you've done the sensors for our standard 4-door saloon, and now we want it for a 2-door, we want it for an SUV, a convertible, that changes the system just enough. It's the same basic control system, but the sensors are slightly different. So the approach now is to train a neural network on all of the data that's been collected from various test drives and things. And what they found is that simplifies the code a lot. It reduces the actual amount of code that's being put into the cars. And you can reuse, once you've defined a basic model using machine learning, you can re-parameterize it to take account of the different vehicle versions in the manufacturer's product range. So it simplifies the whole quality system. You can argue about a model once and then redeploy it several times. So that saves costs as well. So what people are finding in many organizations is that the data scientists who understand how to train and define AI models and work with the data, they typically don't have the skills for developing embedded systems. They don't have the low-level programming and integration and test skills. And similarly, the embedded guys who've been working on this for ages, they don't understand how to work with machine learning models. So what we're looking for is how do we bridge those two worlds in order to bring the benefits of machine learning into industrial production systems. And I'm sure it will surprise no one to know that ETAS has developed a tool called Embedded AI Coder, which attempts to solve this problem. So I apologize, I'm talking about one specific tool here, but I hope the techniques and the action items that come out of it are interesting and relevant across a lot of industrial projects, irrespective of the application. So when we're looking at saying, how do you use a tool to take an abstract AI or machine learning algorithm and use it in a production system where it can be trusted by the operators and passengers and pedestrians and everybody else in the environment. So one of the most important things is we want that code to be safe. We've developed our AI algorithm, trained it, tested it, effectively in the cloud or on a desktop environment where the computing resources available are very different to the system where it's going to be deployed and operate day to day. So we want to know that the code is numerically correct. It's equivalent on the embedded device compared to the environment where it was tested. We want to know that when it uses memory, it's using that memory safely. We don't have infinite amounts of memory in an embedded system. So we want to make sure we don't violate any of the well-known memory problems that can arise. And we want that code to obey guidelines that have existed for a long time, like MISRA. So the thing about guidelines like MISRA is not a prescriptive way to say you must do this. It's a way to make you think, if you're in a situation where you need to break the guideline, can you argue about it and justify why this exception makes sense? So ideally, you want code that says, okay, here's MISRA guideline 123, it's violated here, and this is why. So that anybody who's reviewing that code and has to look at it as a safety or quality inspector can understand what's going on. The second part of this is that if we're using AI techniques to replace functions in a working system, we can also use them to test those functions. So having a tool that says, right, I'm generating some code from a model, turning that into something you can use in your system. It can also generate a test suite to say, look, here's evidence that the generated code works as intended. And the next step from that is to provide test reports and safety manuals for qualification to make the whole thing easier to work with and simplify the lives of people who are using it. So that builds trust and confidence in the use of these kind of machine learning systems. And then, as I mentioned, re-parameterization is increasingly becoming important because people have got a range of similar, subtly different products, and they want to say, we've built this model controlling them, but we need to be able to deploy that model multiple times and just change the parameters of the system and be confident that everything else still works as intended. So how do we go about doing that? So firstly, proof of the correct code generation. So if we have a desktop or a cloud-based modeling tool, some system where you're training your AI model, you've got some validation data that you've reserved from your training, you run that through your created model, and you see the predicted outputs. What you want to be able to do is take a tool that turns that model into embedded code, use the same validation data run it through the generated model, and see exactly the same results, or at least exactly the same within the limits of the floating point tolerance on your chosen processor. So the tool should be able to recognize that any model is a sequence of operations. You're applying input data, you're multiplying vectors of those data with weights. That goes through several layers in a neural network or in some sort of Gaussian regression. So at each stage, you should be able to say, what were the results we saw in the control system, the master system, and what are the results we're seeing in this generated embedded system? And the tool should be able to say, look, here's evidence that it's giving you the numerically correct solution. So you've got confidence it's doing the right thing. So then the variant handling that I described, the idea is you've built a model to do a particular task. That model needs to be deployed across a range of similar systems. So the model architecture remains the same. The training data is going to be slightly different, in this case because the sensors on the bumpers of the cars are at slightly different heights. They need to classify the shape, the position of objects. They'll do that slightly differently. But and that leads to AI model parameters that are different. So we've got the same algorithm, but different parameters. So that means the C code stays unchanged across all of the product range. We're only changing the parameters. And provided you're confident you've done the training correctly, you're seeing the right results, then re-parameterizing the code becomes simple because we're used these days to doing software updates in vehicles either on the production line or over the air once they're in service. That becomes something where we can take advantage of other standards in industry to say, right, we can roll out changes in the parameters either to improve the performance, to fix problems, or to enable new use cases across a range of products. Okay, the next stage to consider is how do you know you've chosen a model that's actually going to work in the embedded system? So one of the things any AI training tool should be able to do is say, there's more than one way to model this system. We can come up with a range of possible models, and we can look at those models in a graph and what's called the Pareto front. So unfortunately, what's missed from this graph is there should be a whole cloud of points here representing different models with different inference times, i.e. how fast they perform, and different amounts of RAM usage, so how much space they're going to take up in your embedded system. And the Pareto front is basically saying which models show minimum out of those two dimensions. So if we've got a runtime critical model where we want something to execute as fast as possible, so something like the braking systems, as Dominic mentioned, you want to choose a model that's got very fast computation time. And the trade-off's likely to be that you'll need more RAM in your system to do that. If you're doing a different model, it might be something to do with health monitoring or condition monitoring. If you think of a truck driving from London to Glasgow, you've got a certain amount of memory available to store condition monitoring values for that. You might want to say, right, we want a memory efficient model, but I'm happy for it to take longer to execute. So using this kind of graph, you can pick out a model that fits into what's important in the space available in your embedded system. So nobody's ever come to me and said, James, I've got all this free RAM in my system, come and help me fill it up. Usually it's very much the opposite. They're saying, how can I fit something in? So if somebody comes to you and says, right, we've had this great idea for an AI technique to solve a problem, if you're the project manager of an embedded system, you're going to say, well, will it fit? Have I got enough code space? Have I got enough RAM? Have I got enough free execution time in my scheduler to actually fit this model in? So ideally, you want to have tools that help you select a model that's going to fit into your system. And here's an example from our tool. So here we've got a model that's a neural network. It's got 9 different layers of weights, and it can break it down and tell you how many CPU cycles you need for each layer, how much RAM, how much ROM you need to do that, so you can choose which model is going to fit into your system and potentially go back to the development team and say, actually, layer 4 here looks like it's taking up a lot of space. Can you do something better for me? So one of the key things to do with that is dot products of matrices and vectors, and there's techniques we can use to speed that up from an embedded point of view. So for example, if you want to do things like clamping values to a certain size limit, if you look at a typical tool that generates ANSI C library code, it's quite simple. You're comparing your input value to a minimum and maximum and seeing where it naturally fits. That takes a certain number of assembler instructions. That's a certain amount of runtime used up in your system. But if you've got a tool that understands which processor it's actually going to be deployed on, it can look and say, there's actually a really nice instruction set that the guys at ARM have put a lot of effort into doing something, so we can do that operation in a single instruction and thereby save an amount of execution time. And similarly, when you're thinking about loading up data to do dot products, you can take advantage of all the available registers, load up more data than you actually need so that you can efficiently process the dot products. And we've seen this reducing the memory loads significantly, up to a third in many cases. So again, you can have confidence that the model will fit into the parameters of your embedded system. Another important thing is looking at memory safety. So if we look again at saying we've got a number of operations, you're putting out the inputs and outputs in a typical memory stack. If the tool knows when you've finished with areas of memory, it can reuse those areas for subsequent operations and therefore reduce the amount of RAM that you need for the stack in your application. So again, it's giving you confidence that you can fit this model in to the runtime environment. And that can give you savings up to 50%. We're working with a lot of the well-known processor companies to make sure we're supporting their chips, which are typically the ones being used in systems today. It's always great to hear about the new developments and the new features that are coming out to support AI processing. But at the moment, those are very high cost, and they're not making their way into the next generation of vehicles that we're all going to be driving. Okay, so as I say, this is a tool that's come from Bosch. It's come from very much a safety-critical mindset. It's already being used not just in the cars that you're driving, but also in kitchen appliances. As I said, semiconductor handling systems, power tools, things like that. So again, you can have confidence that it's proven in use across multiple domains. It's not a one-trick pony designed to solve a very narrow focus problem. So apologies for overrunning a little bit. That's me. I'll be happy to take questions now or later on in the break, as you like.